Okay, let's look at this extension 2 question from 2003, and I think it's one of the most complicated integration questions in 4U you can ever get. So let's read the question first. Suppose that pi could be written in the form of p over q, that is supposing that it's a rational number, and it's a classic by contradiction question because the way they assume pi to be a rational number, which we all know that it really isn't, is to prove that it's actually a irrational number. And you know there's this complex integral, and you need to know that p is actually the same as this p, so they are the same. And you can, since you're using proof by contradiction, you can use the pi as this p over q. Now the first question is use integration to show this. It's very apparent that you need to use by parts, but the tricky part is probably for this type of complex questions, 3 mark, you might need to do it twice. I'm just adjusting my camera because it's a bit weird. Why doesn't it capture me in the center? Okay, it's good now. The second question, by writing it as something, if you do a lot of question, you know that it's splitting the integral, and you can probably cancel out or combine 2 terms. The third one, explain why it's an integer, it's 1 mark, so explanation question. This one, prove this stuff. I think it's an inequality of an integral. It's like and it's also a bound of the integral, upper bound and lower bound, so it's either determining the value or proving it as a contradiction. The last one is actually easy. Actually, if you don't do these questions, you don't do the first questions, you can do the last one, because for all these complex questions, I strongly recommend you to read the question or the sub-questions first, because if you do that, you won't make silly mistakes and you know what the question is asking for. So why is this a contradiction? Because it clearly says that in it is an integer, and if this is more than 1, if n is sufficiently large, and this thing is greater than in, then in is smaller than 1, and it actually cannot be an integer. So it's contradiction, so pi is actually can't be written as p over q, so it's irrational. Now let's do these questions. So I wrote here that these two are very complex algebra. I wouldn't say that you can't do it, you just need to be super careful about these algebra, but ultimately you can do it with enough time. However, I would recommend you to skip them and do these questions, which demand less algebra and they're easy to do. After you be able to do them, you can then come back to these 2, 1 and 2. But since this is not in exam condition, I'm not gonna do that, so let's dive into it. First one, we start with the LHS. Wait, how do I zoom in? Let me see if I can zoom in or not. Okay, I'm not good with the PPT yet, so probably not now. No, I do not think I know how to zoom in, so let's just look at this. For this type, I recommend using this, explicitly write out u and v. So u is the power of n stuff, and v is the cos stuff. It's very different 2 functions, so you set it up like this, and you diff u and you integrate it. It's quite easy, and you get to this step. So now, yeah, I actually forget one more bracket here, but it doesn't really matter. And now that we reach to this step, you will find out that it's still not our desired result in the LHS, so we need to do it again. And the way we do it this time is we actually treat this as a as an integral by itself, because you can't have sine and these polynomial functions mix up, so you have to diff this very complex stuff, which is why I said it's tedious, it's very demanding for 3 mark, and you again use by parts, and then you simplify, you plug in the values. Here is 0, 0, very nice and neat. And now after you simplify, you put the coefficients in. I mean, you need to be actually careful with these coefficients, and I suggest you don't put it in before it's the last step, otherwise you mix up. For example, you multiply this and this, but you forget this and this, then the whole thing is wrong and it's hard to check as well. And last step, you put the coefficient into the bracket and you get the right hand side. So let's look at the second question. So you should know this. It's very common technique, and the reason they do it is because they can make it all nice and tidy power of this without the x squared term. Now let's look at question 3. It's actually quite easy because it's a recursive relation we get in question 2, and I use induction, but it's 1 mark and explain briefly, so you don't need it, but induction is never wrong. So one way is by induction, you just say it's integer, and basically by recursive relation, the first two, they're both integer. The first two, they're both integer. You need to calculate it. After you calculate the I0 and I1, I0 and I1, they're all integer, and the coefficients are all integer. So I3 is integer, etc., etc. So by the recursive formula and by the initial case, and since the coefficients in the recursive formula, they're all integer, so all in will be an integer. And you can do it by induction. They have like the same gist. It's just a bit of more wording and more precise and more conclusive. So yes, it's all, basically what I'm saying is they're all integer coefficients and they have integer start case, so that's it. So yeah, that's what you should do for 1 marker. This is what you should do. I'm sorry I can't zoom in, I'm not familiar with the software. And basically saying I2 is a integer and etc., what I just said. Okay, and now we reach question 4. It should be question 4, my bad. We're proving this upper bound and lower bound for an integral. It is a very common question, and it's also very important because you get to know the limit, which you can use the squeeze theorem, or in this case you can disprove the assumption. So here, first we need to prove it's greater than 1, which is fairly easy to prove because you know this stuff, it is positive, and if it's positive then the whole thing is going to be positive, and you need to show it's smaller than this stuff as well. So of course, as usual, we start from here, we square, how do I erase this? Okay, we start from this, then we square root it, then we have this, and now we can break up, for the integral we can break up this because we have an upper bound and a lower bound for this. Now we can basically say it's this and this, we can get rid of this into just a number, and if you just integrate below a number, it's like a error in a straight line, horizontal straight line, and it's very easy, right? So you get this 2, you get step blah 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 blah, you just reach the last step, and I think you can do it. It's not very difficult question, and it's also a common technique to use this from the boundary conditions. The last question I talked about it in the beginning is just by contradiction, because it should be an integer but it's smaller than 1, so it's a contradiction, so pi is irrational. And last but not least, if you mention the, I mean, I'm not sure, but pi squared over 4 is not a coincidence, I think. Although I don't have any proofs for this, I don't have any, like, just by intuition, this is a well-known result. I think if I memorize it correctly, it should be like this. I'm 99% sure it's true. So the reason why this is here, it just makes me feel that it's quite interesting, but I don't know why it's here. And my next question is gonna be on how to prove this Basel question purely using extension to math question, and it's possible as long as you use some complex. Complex is basically all and polynomial. You can prove this and you will make an excellent Q16C question. And that's the first video, I mean, after a fairly long time, and I hope you enjoyed it. And it's day one, and I'll keep posting day 2, day 3, day 5 continuously, and hope people would enjoy it. And that's all for today, and see you next video.